Well, good morning, everyone. Welcome to the second day of our webinar series on airship corridors and gateways to the Arctic. I'm very pleased you can be with us today, and we have a great program lined up for you, as you will see shortly. Before we get started, I just want to again let you know about the in-person conference on airships that's coming up in September, the end of September, in Nuremberg in Germany. Dr. Flum, who was with us yesterday and is here today as a delegate, is going to be organizing, or is organizing this, I should say, and it should be a really great opportunity to meet people in person if you have an opportunity to go to Germany and see this. And as you can see, the focus is going to be on electric airships. Certainly one of the strengths of this industry is that it's not difficult for airships to convert to electric power and have zero carbon emissions, which is pretty impressive for aviation. In any case, at this point, I'm going to stop sharing, and I'm going to introduce our first speaker, Eli Dourado. Eli Dourado is a senior research fellow at the Center for Growth and Opportunity at Utah State University. His work focuses on identifying and eliminating the barriers to hard technology innovations needed to drive large increases in economic growth. That sounds like airships to me, Eli. He has worked on a wide range of issue areas, including geothermal energy, permitting, aviation, space, and cryptocurrency. His popular writing has appeared in the New York Times, the Wall Street Journal, the Washington Post, and Foreign Policy, among other outlets. He holds a PhD in economics from George Mason University and a BA in economics and political science from Furman University. And his topic is the big picture. How appropriate. Thank you very much for joining us, Eli, and the floor is yours.
Thank you, Barry. I am delighted to be here with you all today to talk about airships, which I think have enormous potential, including a major economic potential. In short, I like to summarize it by saying airships could be big, which, as you'll see, is a bit of a pun. I'd like to start by talking about how domestic freight moves in the United States. So we have a bunch of different modes that are used domestically in the United States. But as you can see, the lion's share of it is taken by trucks. So all these modes have different qualities, they have different price points, they have different latencies in terms of how long it takes goods to get to your destination from when you start out. And a tiny percentage of the value goes by air, and even smaller percentage of the tonnage goes by air. Some goes by water. The US has great intercoastal waterways. Of course, rail is a piece of it, but trucks are just an enormous, a staggering proportion of it. And so, what would this look like if we got rid of the roads and the rails and the pipelines, right? What would this look like? And we can sort of get a picture of what that would look like by looking at international freight to and from the US, but excluding Canada and Mexico. So that's what this chart shows, is that most of the international freight coming in and out of the US, not counting Canada and Mexico, which are connected by land, travels over water. Both the vast majority of the tonnage and the majority, but not an overwhelming majority of the value, and quite a lot of the value still comes by air, and there's other things that are rounding errors. And so we can sort of picture what would happen if we introduced a new mode of freight that could operate internationally over the oceans that had the characteristics of trucking. So what if it had the sort of the cost price point per ton kilometer of trucking, and it had the sort of the delivery time? Instead of, you can send something overnight by air internationally, or you can send it over on a container ship that'll take you about 2 months to get to your destination. If you can sort of have a few days to a week latency and sort of a trucking price point, that we would expect would take the lion's share of the international cargo market. So that is a big market, right? So if you look at containerized international maritime trade, that is 13 trillion ton kilometers. So that is quite an enormous market. And to put a fine point on it, let's say you were able to take half of that market at 10 cents per ton kilometer, which, to be clear, is upselling a lot of the container ships market, because they pay a lot less than that. But you say, we can get your goods there in a week, and similar to trucking economics, would you do it? And, again, this is excluding bulk carriers, this is excluding the ore carriers, the liquid container ships, liquid fuel ships. Just the container market at 10 cents per ton kilometer is $650 billion of annual revenue. If you could do this as one company, you would be the biggest company in the world by revenue. And I think this is by far the biggest market that airships could potentially address someday. I can't think of a bigger one, at least. Maybe you can. So how do we get there? To meet the trucking level economics, we have to think bigger. And so size clearly matters. As we all know, airships have wonderful performance scaling as they get bigger. In fact, it's very seductive to me to think about this. So we all know that lift is proportional to volume, which is, for a given fineness ratio, is going to scale with length cubed. Drag is proportional to some linear combination of cross-sectional area and wetted area, which is proportional to length squared. So we have L over D scaling with a cubic term over a squared term. So L over D scales with length. Perhaps the scaling is even better than that if you're talking about a rigid body airship, where the structure becomes a smaller fraction of empty weight as the airship gets bigger. So it's better than square cube even. And so some collaborators, co-conspirators of mine and I came together, and we thought about what could this actually look like? What would be something that could potentially address this market? And here's what we came up with. We said, the payload range needs to be 500 metric tons at, able to go 12,000 kilometers, able to cross the Pacific. At that size, we really were kind of locked into rigid body if we didn't want any exotic materials in the design. And we got an airship that was 388 meters long, that had a gas volume of over 1 million cubic meters. It had gross weight, counting fuel and cargo, of about 1 million kilograms. So this would be, I think, by any metric, if it were built, it would be the biggest flying object in history. Not the biggest one ever designed, interestingly, but the biggest one that was, if it were built, it would be the biggest thing ever built that flew. So what would the demand be for this ship, right? If we assume, again, half the container market, that is 25,000 aircraft of this kind, which would put you, that's about the same as the number of airliners operating in the world today. So it's just, just for scale, it's just a massive market would be demanded for this airship if it existed. So I'd like to talk about a few interesting design considerations that we thought about while we were doing this. Again, designing an airship specifically to serve this market, the international cargo container market. And the first is autonomy. If you are flying, trans-Pacific on one of these airships, they don't go that fast. It would take several days to cross the Pacific. You would need not just one crew if you were trying to do it manned, but you would need several crews. You would need bunks, galleys, labs, a lot of onboard infrastructure to accommodate these crews. And if you can, design the aircraft to be autonomous or at least remotely piloted, you can delete a lot of those parts. You can really simplify and reduce a lot of the demands that would complexify your design. And so, autonomy is I think a perfect match for this kind of market, for this kind of aircraft. It's relatively slow moving. We know how to do satellite links. We could do triple redundant satellite links if necessary. And I think it could certainly be made autonomous. The next consideration is, what is your lifting gas? And I think if you're thinking about a scale, this kind of scale, 1 million cubic meters, 25,000 of these airships, hydrogen is really the only game in town. There is not that much helium on the market today to service the demands of this concept. And so it's got to be hydrogen. We're going to have to win over the regulators to do it. Hydrogen also has the virtue of being much cheaper than helium, has the virtue of being, so cheap that you could vent it if you wanted to. It has the virtue also of having 8% higher gross lift. And so that reduces improves the economics further relative to helium. So it's got to be hydrogen, I think, for this to work. A third consideration that's really important is manufacturability. So if you are designing an airship to be built not just once as a bespoke, perfect Fabergé egg of an airship, but mass manufactured, right? You really need to design for simplicity and manufacturability. You want to delete as many parts as possible, make it as simple as possible, use welding rather than other more complex manufacturing techniques as much as possible. And so that's going to have to factor into your design. An additional consideration is winds. Airships travel relatively slowly as a fraction of the headwinds that they might face. And so headwinds are just extremely detrimental to transport efficiency for airships. And so this might mean that you want to slightly overpower the airship relative to what you naively would like to do, but headwinds are very challenging. The thing that we have today that is much better than the previous age of airships is much better weather prediction. So we'd want to avoid inclement weather, certainly tropical storms, hurricanes, et cetera, but also maybe other storms. And if we also have that kind of weather prediction built into our operations at a fundamental level, we might want to optimize for wind. So if headwinds are really damaging to transport efficiency, tailwinds are wonderful for transport efficiency. And so you would want to design the route to, dynamically, constantly redesigning the route dynamically to take advantage of tailwinds and to maybe go significantly out of your way from a great circle path to get to your destination. And this means, we'd be bringing back a form of sailing for the 21st century. Sail the winds on your airship to get it to its destination with the least amount of fuel use in a good amount of time. Buoyancy control is another very challenging problem for airships. So again, I've suggested we should use only hydrogen as a lifting gas, and that would enable venting. So if you needed to get a little lower, particularly as you burn off fuel, you could do that through venting. Another approach that I think is very much worthwhile to consider is vectored thrust. So you'd want to have propellers on board that you could vector in any direction. And particularly you could point them up if you needed to get a little bit of extra altitude to, say, go over a mountain, or if you or you could point them down if you wanted to land at the end of the journey, and so reduce the amount of venting that is necessary. There's another concept for buoyancy control that's gone around the airship industry for a long time, and that is compressing the lifting gas. And I done a bit of math on that, and I think the compressor efficiency and lightness and reliability and the power requirements are just are kind of significant if you're talking about compressing a significant portion of the lifting gas for that. Hangering, again, if you're starting from the assumption that we're going to have 25,000 of these airships operating transoceanically, are we going to have a hangar for each of them? I think the answer is probably not. So 25,000 hangars that are bigger than the hangars that we've built in the past for airships is quite a lot. And so these craft need to be built to be weatherized, at least when fully moored and fully ballasted on the ground. When so they need to be able to be stored on the ground in sort of the open. And if you can't do that, that's an added complication for sure. I think another open question is, can you build these things without a hangar? So if you look at cargo container ships, oceanic container ships, they are built, they're about the same size and they are built in the open. They're not built in the equivalent of hangars very often. So so figuring out how to build these things in the open is would be valuable, especially if you're going to be building many thousands of them, as I've suggested. So those are some considerations. I think none of those are, some people might disagree, but I think none of those are that hard. I mean, they're considerations that must be addressed. But when I think about why this is actually hard, I think of it a few things. So one of them is that I think the imperative to have iterative design. If you look at, say, aerospace startups, and what is the biggest predictor of success? I think an enormous one is how quickly did it take them to get something flying? So this is, I think, most clearly shown if you look at, say, do a comparison to, say, between SpaceX and Blue Origin. And the two companies took completely different design approaches. SpaceX took an iterative approach where they flew something quickly, whereas Blue Origin designed a rocket very thoroughly and expected it to work the first time. And so the SpaceX model, where they actually had failed launches, their first 3 launches with the Falcon 1, has proven to be a superior model, I think. And so doing that with airships is very hard, especially if you're doing it with a 500-ton airship. So so you have to build a massive ship from the beginning. When you've raised your say your seed funds, very quickly try to build something that's at least representative. Very hard to do. Secondly, you have the subscale problems. So a very common thing to do in aerospace is to have a subscale prototype. And just as the square cube law is so seductive when you're going bigger, it is equally detrimental when you're going smaller. And so building a representative airship that is designed to de-risk some aspects of the international container airship market with a prototype that is smaller, it's very challenging. You're not going to be able to do it that small and have it be representative in any way. I think another challenge is that type certification gates revenue service. So you cannot be earning money with your prototypes. So you have to build prototypes that are only used for testing and cannot be used to make money, at least in the US. And I assume something similar holds with Transport Canada as it does with FAA rules. And so there are potentially countries that might allow you to operate your prototypes for money. And so that's worth exploring. But I think that is just a massive challenge. And of course, type certification can cost a lot of money particularly if you're building a novel aircraft, as I've suggested. And last, I want to discuss the siren song of beachhead markets. We all know that there are markets where the revenue that you can earn on them is higher than, say, 10 cents per ton kilometer. And so it's very tempting to design an airship to target those markets. I think that this is a mistake because the airship that you ultimately want is very different than the airship that you would design for specifically for those markets. And so the right approach is to design an airship for this extremely enormous lucrative market, and then operate it in the beachhead markets initially. But don't design the airship for the beachhead market because then you won't have something. You'll have something that maybe can only serve those beachhead markets and can't and can't serve the international cargo market where the 650 billion in annual revenue lies. And so that leads me to a concluding question, which is, can a 500-ton airship be funded? And I think the answer is it would be very challenging. So to fund it, certainly to fund it through traditional venture means, I think would be very hard. The way what I would call hard tech venture works is that you raise the money, you de-risk a significant part of the problem, then you go out and you raise a bigger sum of money at a higher valuation because you've de-risked, it's now a less risky investment. And then you go and de-risk a bigger chunk of it, and you can raise even more money at a even higher valuation, and so on until you have de-risked the entire project, and then you can raise the last amount that you need to build the final product that you need. With airships, I think actually an enormous part of the de-risking happens at the very end in the operations stage. So you have to kind of pay for type certification, which could be $1 billion, while still having all the risks of the operating model not being proven, right? So not being able to demonstrate that you can the logistics of running this business make sense. And so so I think it's very hard to do from a venture funding model to do it to fund this kind of project. I've been looking more into sort of NASA models for funding aerospace development. And in particular, there's a commercial orbital transportation systems contract that NASA signed with SpaceX to fund the development of Falcon 9. And that was a very interesting model because NASA did not pay the entire cost of the development. They paid a portion of it because SpaceX was going to end up with a commercial article at the end. So to make sure that your subsidy isn't wasted, you need to make sure that that the manufacturer has some skin in the game. It was also a milestone-based contract, so they didn't get the entire sum up front. They got some sums as certain milestones were hit, and it was also a fixed price contract, so that SpaceX had an incentive to keep costs down, keep a lid on costs, and you didn't have all the usual problems that we have in the aerospace industry with cost plus developments. And I think something like that, if we had a NASA style program to develop a 500-ton or more airship that could with at least trans-Pacific range, I think that would be the model that would have to be used to sort of fund the initial development of this, at least until the business model is de-risked. So that my hopes for this are pinned significantly on sort of that collaboration with aerospace science agencies, either NASA or their counterparts in other countries. So I believe I'm at time or over time, so I will stop there for, I believe Barry has allotted some Q&A time, so be happy to stop there and field questions at this time.
Thank you very much, Eli. That's a great presentation, and certainly your title was not exaggerating. It is the big picture. I just did a quick calculation that a 388 meter long airship at a 6-to-1 fineness ratio would be 65 meters in diameter. So that would be a very big hangar indeed. Not something we can't do, but certainly it would be a colossal hangar. One of the questions that I think the audience may have as well would be, well, what would be the first commodity you'd look at for moving in these containers? What would you take away from the containers first, or the container ships first?
I think so. I think you would want to service wherever the highest dollar per ton kilometer would be first, right? So even though the beachhead markets are, I think, seductive in a detrimental way if you're designing for them, you'd still go after whatever the most lucrative thing is. So it might be some remote service or some or some other sort of exotic windmill blades or something like that. But in terms of the actual shipping market, I think what you would target would be would probably be the highest value goods that still go in terms of value density that still go by ships, which I understand is probably something like machinery. So things like tractors and other kinds of machinery. So that would probably be the first thing to come on airships rather than on ships, because they aren't value dense enough for planes, but for ships it would work great.
Yeah,
or for airships it would work great.
Certainly things that would be low density would also certainly have some appeal as well, because oftentimes freight bulks out before it weighs out. So those sorts of things may also be attractive. There's a question that came in. Any idea what the price would be for an airship that big? I mean, there's a real finger in the air, I'm sure, but I'll put it
yeah. So I think this is something we had a very hard time doing. It was estimating the price. And certainly you could look at the materials, like what are the materials cost, and it ends up being, if you're only factoring the materials cost, it ends up being pretty cheap, and on the order of $10 million or something like that, for the airship. You have to factor in, of course, the design overhead and the labor overhead and all that stuff. I think that the first one comes in at, probably come in at quite expensive. You're paying the certification costs, which I've said could be over $1 billion. But again, designing for simplicity, trying to make this as manufacturable as possible, you could potentially make it very cheap on your 1,000th unit. Could be very cheap indeed. And that's really what you need to do to get the price down, the price point down to something that is comparable to trucking.
One of the things that you mentioned, is this idea of NASA has invested. I mean, long before SpaceX got involved, NASA had spent 50 years investing in all kinds of science to send rockets and landing a man on the moon and so on. And certainly in the case of aviation, huge amounts of investment from government went into fixed-wing aircraft. There's been very little going into airships. What would it take to get the government to be engaged, not just in the US, but I guess worldwide, in airships?
Yeah, so you need politicians to feel that they have some stake in the airship business. I think it is possible to get members of Congress excited about airships and sort of to start allocating. I would say actually that the NASA aeronautics budget is very small relative to the NASA space budget, right? So even getting NASA aeronautics to get more funding, and I'm sure it's the same in other aerospace agencies. So getting more investment in aeronautics generally, and then earmarking some of that for airships, I think is the right approach. Then again, this is not advanced science. This is 100-year-old technology for the most part, right? I think what we mainly need is de-risking in terms of funding the actual building and the development of these aircraft.
I always say it's not rocket science; it's just balloon science. But in any case,
yes,
maybe that's part of it. It doesn't have the flair or the jazz of cutting edge, although I think what you're talking about certainly does. Another question that came in was the notion of remotely piloted airships. Certainly makes a lot of sense from an economic perspective, just weight and space and labor and what have you. Would this lead, do you believe, to lower costs for certification as well?
Oh, I think that autonomy probably adds a little bit of costs to certification, because you have to have multiple, like, redundancy in a lot of the comms, for example, the links and so on. It may lower costs in some in at some margins, because you don't have a crew on board, right? And so you don't have to worry about crew safety at all, right? And so I think that's one thing that would help you get hydrogen lifting gas on board, right? If you look at the Hindenburg incident The vast majority, all but one of the people who died were on board the ship. And so yes, I think it adds some certification costs in terms of command and control, and sort of course the control laws and so on would have to be certified. But it would lower the costs in terms of not having to design for a human on board.
Well, Eli, thank you so much. I noticed that we are now stretching into past the time, and you did mention about hydrogen. And just so everyone in the audience is aware on your schedule, the last speaker of the morning is going to talk about this issue of regulations and hydrogen, and certainly what's been happening in Europe in terms of airship regulations. So again, thank you so much for being with us. I hope that you can stay for some of the rest of the presentation. So again, Eli, thank you so much for being with us this morning. And again, appreciate you taking the time to do this.
Thank you. It's been my pleasure.
Right, you are. I'm now going to move on to our next speaker, who is Tom Grundy. And Tom is, you could say, is really in there doing it. He's not just watching or thinking about it. Tom Grundy is the CEO of Hybrid Air Vehicles Limited, the company behind the Airlander. Tom and his team at HAV have been changing the way we fly and certainly rethinking the skies to provide new opportunities to combat the impact of climate change. Tom's technical expertise, resolve, and understanding means he brings an engineering mindset to the net zero challenge and is driven by responsibility to drive change in the aviation industry. He holds an MBA and a master's degree in aerospace engineering and advanced systems engineering. He's a chartered engineer and a fellow of the Royal Aeronautic Society. And thank you so much for joining us today from the UK, Tom, and we appreciate you being here.
It's an absolute pleasure, Barry. It's great to be here and to have the chance to talk to everybody about what we're doing here at Hybrid Air Vehicles. So thank you. It's an exciting time for HAV and the Airlander program. So, but I think it's also a pretty exciting time for the sector as a whole. There's something of a resurgence of interest driven by a number of factors, and certainly we at HAV are working hard to make sure that Airlander really enters the market quickly and enters the market well. Really is the start of that resurgence. So fascinating just to listen to the previous speaker, Eli. There's a lot there that I think our experience of bringing Airlander to the market really chimes with some of the blockers, some of the questions, some of the thinking that needs to be done to get into the market. And there are some areas where, in what I talk through over the next 10, 15 minutes or so, where we've found ways around some of those challenges that Eli outlined. So some really interesting thinking and counterpoints there, and hope to draw some of those out as I speak.
Yeah, we're coming through beautifully.
Very good. Thank you very much. So Airlander is a hybrid aircraft. You can see it there flying in the UK in 2017. That's our full-scale prototype aircraft. It's 92 meters long, designed to have a payload capacity of 10 tons in service. We took it through really 3 phases of flight test to get it to the point of maturity it is now. Initial flying done with the United States Department of Defense in around about 2012, 2013, and then 2 successive rounds of flight test of aircraft with progressively modifications, so iterating that design, iterating the approach to operating it in airspace. We moved from military airspace in first flights to Class G airspace under EASA and CAA permit to fly in the picture that you can see there. It's a very low emissions aircraft. Obviously, everything in our sector comes with the benefit of a big head start against gravity. In our case with Airlander, we take about just over half of the lift comes from buoyancy. So the part that makes it a hybrid is that, as well as a buoyant aircraft, it's a lifting wing. So we get a much greater proportion of Airlander's lift in flight from aerodynamics than is the case for a traditional airship. It means a couple of things. It means that we carry much of that airship-like efficiency. So kerosene-fueled prototype there, that's flying on about or delivering about a 75% reduction in emissions, which is obviously a key metric for many of the markets that we're moving Airlander into. So that's just from the benefit of using helium to essentially to offset the empty weight of the aeroplane. We then use aerodynamics to do the rest of the lift. The other implication of that is that the buoyancy challenge is significantly mitigated for a hybrid, because we can turn off 40% of the aircraft's lift simply by stopping the engines. So that buoyancy challenge that I referred to, that we'll think about a lot, gets significantly simplified by the hybrid. And then, of course, the other thing is it operates from the ground. So it takes off and lands. So the practical aspects of loading and unloading passengers, fuel, freight, maintaining the aeroplane, they're somewhat alleviated by the fact that the aircraft's on the ground while we're managing it. As a byproduct, that means the aircraft is much less constrained by infrastructure than traditional aircraft. Again, a common theme to a lot of the thinking and a lot of the developers in this forum. And we're finding particular resonance in the market, even in things like passenger operations, for the ability to go away from traditional airfield infrastructure, to be able to operate from unprepared areas, much in the way that helicopters do, to be able to unload and load passengers in parts of the world that are hard to get to right now, and also to upscale the capability of existing infrastructure. So we work with potential customers and people looking at the product in parts of the world where their airfields at the moment are perhaps capable of taking a 19-seat aircraft, really very little capacity for cargo. And we can work to take that same infrastructure with very minor modifications to that infrastructure and start delivering large-scale loads into that environment. Mike Durham, our technical director, our CTO, has spoken to this forum before, so I won't go too much into the technology behind Airlander, but suffice to say, I've given you the major points there. It's a non-rigid, so there's no rigid structure on board. We conceive of it as a family. So our path to market starts with a 10-ton capacity aircraft. We then move on to a 50-ton, and we believe that the non-rigid technologies that we've laid down here will take us to 200 or more tons lift. We've looked at aircraft as big as the ones that Eli was talking about in the last presentation. And one of the ways that we're looking to unlock the market is by making sure we have a common design at each of those levels, 10, 50, and 200 tons, that's applicable into multiple markets. So rather than, I think that beachhead challenge is a real one, and really that's what I'd like to unpack a little bit, how we're thinking about that in the next, in the rest of my presentation. So where I want to start with that and think about markets is just to point out actually that in my experience, a lot of the things that I think will be very clear to people in this forum perhaps aren't so well understood in the wider world. And this picture is what we often use really to explain that to people who are coming across this sort of technology for the first time. And it's a very simplified treatment of really of a transport efficiency question. And all it's doing is really working to expose to people and into people's minds the fact that our transport solutions today really are bifurcated between fast and relatively energy intensive aircraft, albeit with high transport efficiency, and then our slower and more infrastructure dependent surface transport options, trucks, rail, shipping, and the like. And we just work with our potential customers just to open their understanding that there is a very big gap between those two options, and it's exactly the gap that the previous speaker identified. He said, well, actually, when you're in continental United States, trucking dominates. It doesn't dominate where there are obstacles in the way, because we've got a gap in our transport infrastructure that we haven't figured out a way to fill yet with the equivalent transport efficiency of the other options that we can use today. So this is really our picture that explains that same dynamic, that there's a big gap here. And the way we conceive of it actually is putting an efficient mode of transport in place at 100 to 200 kilometers an hour, that's the spot to aim for, and that's what we're working to get into with Airlander and the hybrid aircraft, obviously where airships look to play very strongly. The follow-on from that is that I think in our discussions in the market, what we find is there's a lot of tendency to anchor on the things that make jet transport efficient today, and principally speed. And the dynamics of the air freight market are very stark, aren't they? It's about 1% of global trade gets done by air transport, or global logistics and freight transports by air, but it's 35% of the value. And so I think it's very easy to fixate on the value, the time value that you get by spending money on moving freight quickly, and forget that actually that's a really small proportion of the freight that's moving around the world. I mean, I would argue it shouldn't be moving around the world at 500 miles an hour when we're fighting climate change anyway. But beyond that, there's 99% of the freight that's going over the surface by road, by shipping, by rail. And it's that market at the bottom right, that's where these technologies play. And again, I think that's well understood here, so I won't labor on that, other than to say, I think that that's not a perspective that's very widely shared yet in the world. And I think that's an argument that our sector, our industry needs to keep making, and making strongly to make the case for these technologies. And of course, putting something in that gap means there's a whole range of new services in underserved parts of the world, managing around bottlenecks and congestions in today's network without having to build extensive infrastructure to be able to do that. And more importantly, of course, avoiding unnecessary emissions from transport. So given that sort of very broad view of the market, we segment that market then down into three slices. The first of those being logistics, which obviously we've just talked about at length. I think as well as containerized shipping, which I would agree is a job for the very biggest of aircraft. We also see connections at the edge of today's networks as being very important. Canada being a brilliant example, connections to remote communities, connections to mining assets, the ability to actually get from the railhead up to remote parts of the world without needing to put infrastructure in to get there, making those sort of problems that helicopters would really have got to if we could have made them efficient or quiet enough or have long enough range, large enough cargo. These are useful markets in and of their own right, we believe. So part of our thinking is stepping through those markets before getting to the super large aircraft. And we already talked, and Barry talked in the quick Q&A about low density cargoes changing the fact that we that aircraft bulk out before they or get out of volume before they run out of carrying capacity. Changing that dynamic obviously does open new markets. What we're doing here is we're focusing on our Airlander 50 product. That's 50 tons or a little bit more actually of lift, 6 shipping containers in terms of the space on board. We've launched that program with a group of development partners, including AECOM, big infrastructure services firm, wind turbine developers, people building out onshore wind infrastructure, fruit and veg providers looking to access bigger areas of African producing regions, and a regional transport network in Scotland who are really interested here in the UK about creating better connections to places. So that's formed an initial consortium where we're really starting to drive into those requirements, make sure we get Airlander 50 set for the market. Our next market segment, comms and surveillance, using the aircraft's efficiency to fly for very long periods of time, 5 days at a time in the case of Airlander with big mission systems. In our view, that puts this sort of capability at sort of 10 times the capacity for surveillance that we can extract from today's fixed wing aircraft. So this is an interesting market for us. It was the first market that really stepped into investing in the technology. We did initial work here with the United States Department of Defense, helped scale the product, scale the platform, and really prove out some of those long endurance capabilities. For us, that's a very nice adjunct market, it's defense market alongside our commercial markets, with all the benefits that brings. And then the third segment has been one of the most interesting in the early stages of market entry for us. And perhaps I think the most non-obvious when we started this. Airlander 10 tons of lift can be turned to carrying up to 100 passengers. The fact that it can operate away from airfield infrastructure means it opens up connections, or again, can connect 100 passengers, perhaps to airfields that at the moment can only service aircraft capable of carrying 20 or so. And critically, the product delivers a big step down in emissions. So we've really seen this product resonate as the aviation industry has come through the impacts of the pandemic, realized that there are scenarios in which 70% of the fleet can be grounded, perhaps seen really the problems coming in terms of social acceptance of aviation, and particularly in sectors, in transport sectors where other technologies can do the job. So we've seen France move to legislate away from short-haul air transport where it's possible to do so. We're seeing Spain make similar moves. We've got the Nordic, Scandinavian countries setting net zero transport objectives for 2040. That's generating real interest in the regional airline world in what are the alternatives out there. So what we've been able to offer here is 100 seats, better than business class space, operating economics that outperform the aircraft that we've got operating on very short sector routes today, because it's not really an efficient use of regional jets, and a growth vector for those airlines that gives them a growth path that is not linked to emissions. At the moment, all their growth paths deliver straightforward increases in emissions as they go. This gives them a different emissions curve, a different growth path. So launch orders here from Air Nostrum, which is the third biggest regional airline in Europe. They're taking 10 of these aircraft. We expect them in service from 2027. That use will be 100 passenger transport between cities, between the Spanish mainland and the islands and around those regions. We also have a market alongside that in using the aircraft for tourism and leisure. It's big, it's spacious, it's quiet. You can, with the loads that are involved, you can put some really interesting features in there in terms of being able to view horizon to horizon. So again, this market, the aircraft's resonated well in, and we expect our first 3 aircraft to go into these uses fitted out in the sorts of configuration that you can see here. And again, this is very useful to us because this really unhitches people's expectations of what an aircraft is. We're used to 3 abreast seating and squeezing into the middle seat. Obviously, nothing could be further from the truth with a product like this. And again, back to the mobility, the passenger uses, even in airline style seating, you're delivering space to the customer that is above what can be delivered on any other aircraft at the sort of price point that you need to hit to get economy travel and the economy travel offer working. And then the final part of that, and I think the counterintuitive piece for a lot of people as we've gone into this market has been journey time. Obviously, the airline world and the aviation world in general works with speed as its major driver. And speed is not the advantage that we bring to the market with any product based on lighter than air. So what we've really been doing is working to unpack the journey. How many of us, travel to the regional airport, take the time that we need to take to get through that regional airport, through security, to the gate, get on the aircraft, maybe have to then go and get a connecting flight and so on and so forth. So it's really about the end-to-end journey time. And so these examples, there's a number of them on our website, are really designed to just pick apart how much of an advantage speed really is when we're using aircraft on very short sectors. And as you can see from the numbers here, it's not that much of an advantage actually. Total journey time between Barcelona and Palma, 4.5 hours on Airlander, 4 hours, 7 minutes by the flight. The difference there being that you've arrived in Airlander with a 90% reduction in the carbon emissions of that journey. And that message resonates well with the governments who want to have regional air transport working in a net zero future. And of course, the next best alternative, nearly 10 hours on the ferry. So it's these sort of examples that have really helped Airlander move into this part of the market. Now, I just want to return to the point about how do you scale something that inherently needs to be big to be economically viable. And the way we've worked to do it is to create one single aircraft design at the Airlander 10 level that can do all three jobs. So that same aircraft design can be fitted out with 100 seats. It can be fitted out with a 3-ton surveillance payload and crew accommodation for a crew on board, or it can be fitted out with a cabin that's capable of carrying a 10-ton palletized load. And so it's one aircraft design addressing each of those three market segments. And we'll do the same at Airlander 50, one aircraft design with multiple uses. What that's allowing us to do is step our way through markets where revenues can start to flow early, whilst always having an eye on that growth path into larger aircraft and moving more and more into that mainstream logistics market. With the added advantage that a hybrid, because we're getting multiple sources of lift from the same unit of volume, we've got aerodynamic and aerostatic lift, will just be a little bit shorter and a little bit smaller for any given payload. So that's very simply the way that we're pulling together different parts of the market just to move our way through and scale the product towards logistics. We're not doing it on our own. We've built a very strong set of partners alongside us. AECOM, Collins Aerospace are working on electrifying the engines of Airlander. We have operating partners alongside to help initial customers get going with operations. We're also working with local government here in the UK. So alongside our work with Air Nostrum as a launch airline customer, we're working with a consortium in Scotland about early uses of the aircraft up on that Scottish transport sector. And we have the South Yorkshire region of the UK investing to build a production line capable of delivering 12 aircraft a year into the market. That's our initial rate of production, 12 aircraft a year from 2027. So I'm now reaching the end of my allotted time. I'll just let a few photographs of what's behind us, what's got us here, run through while I hand over to Barry for any questions.
Thank you very much, Tom. There are a lot of questions, and some of them are technical and engineering. Notwithstanding your strong engineering background, I don't want to put you on the spot for some of these really more detailed things, but you've mentioned a couple of things that I thought were really interesting. Europe has a lot of peninsulas. There's a lot of water separating places. It seems like an ideal location. And you've mentioned in the past Liverpool, Belfast being a link. And I saw a presentation that looked at Stockholm, Oslo, how difficult it is and how long it takes to actually get there. Obviously, these are the sorts of markets that would make sense. To me, it seems like the passenger market is one that's really waiting for you to develop.
Yeah, I think that chimes with what we're seeing. And I think it's very synergistic, actually, Barry, with what's happening with the electrification of regional aircraft. So there's obviously a very, very strong drive towards trying to move the world's smaller aircraft either onto a battery electric equivalent or I think perhaps in the long term we're looking at hydrogen there, aren't we, for those sort of sizes of aeroplane. It's certainly, in my experience, it's driving a resurgence of interest in what can a good regional airline network look like in various different parts of the world. And Europe is a great example. Of course, the bulk of mainland Europe is very well served by high-speed rail. But as you move out into the margins of the more difficult geographies or to the edges of the more difficult geographies, it's not served by that high-speed rail network. So we form that adjunct there in those parts of the world. We can move low emissions aviation from a mindset of getting to 20 seats, maybe getting to 50, 70 seats by the middle of the next decade. We can move that into a view that actually 100 seats and low emissions is possible now. And I think as you're doing that, your mind then goes to the island nations of the world. It goes to perhaps the 8 out of 10 people in the world that haven't got on an aeroplane yet. How do we start to serve and grow those sort of markets? And it also comes back, I think, some of our most developed markets. There's really interesting work being done by NASA and by some of the universities in the US about the latent potential of the regional airport network in the US that really is now being underutilized as aviation has centered itself in on fewer and fewer hub airports. So opening up and decentralizing even those well-developed networks like in the United States, these are kind of slightly hidden challenges, the things where differences can be made once you demonstrate that actually doing this at scale and doing this with capacity is possible.
Being from Canada, we're always interested in weather, and especially cold weather. Yeah. And by the way, thank you. I appreciate the support letter you gave us regarding the cold weather testing efforts that we're trying to do. But this does raise that issue of cold weather. As a non-rigid, how does that cold temperatures, how do you square that with the gas trying to keep the shape and so on? How difficult is that? Or is that a market you'll be entering later?
No, it's a good question, and no, it's not one that we're saving for later, actually. So really, when you're the driving requirement for us, actually, in terms of managing gas pressure in the aircraft, is climb and descent rates. So, if you're able to manage those pressure differentials and the time constant associated with those, which of course the aircraft's designed to do, then operation in cold weather, the sort of the pressure changes, the different things that the climate can throw you in places like Canada, are well within the design envelope of the airplane. Now, obviously, one of the reasons we wrote you about cold weather testing is we need to go there and prove all aspects of the aircraft operation in cold weather, just as much as we need to go for the hot weather testing at the other end of things. So that's where, as we get into our program, we'll cycle that testing or schedule that testing based on what the first operators need first. But no, expect us to go through the full range of cold weather and hot weather stuff early in the program, because I think for us, in every aspect of what we're doing, we're working just to work through this exactly as the rest of the aerospace world will. The aircraft needs to come off our line with a worldwide clearance.
By the way, we will provide you with a copy of these questions that have come up in the.
Okay.
If you'd like to answer some of them more directly yourself, because we're not going to have time to get to them all. But there have been a couple that dealt with the issue of aerodynamic lift. Does this stay the same as the airships get larger in size? And also, there was a question dealing with the amount of lift that comes as you get bigger. Anyway, if you could address those in some way.
So I don't have the benefits, apologies to whoever asked, I don't have the benefit of having the exact word in the question in front of me, but look, conceptually, so the core thing is there's a mix. So, and one of the design, as in a mix of aerodynamic and aerostatic lift, and it becomes a design parameter in the concept design of any given aeroplane as to what fraction of each you want to design in. And so one of the things that we do is aggregate requirements from all of those three different markets and pull them together to get the best blend of aerodynamic and aerostatic lift for the range of operations that we see any given aircraft go into. So if that sounds like a long answer or a slight obfuscation, it is because it's a design parameter. It's something that we can choose to set down. Does it therefore stay constant as you scale up the airplane? Well, you're looking to access different use cases. Your questions about disposable load versus static load, all those things will feed those into the design process and then design for them. And so, but the concept stays the same. The concept is about creating the best blend of both. So we're taking as much efficiency, which obviously translates into the airborne cost per ton kilometer of the aircraft, whilst keeping enough back for aerostatic lift that we can manage buoyancy, we can deal with buoyancy management easily. And the driving factor there is to minimize ground infrastructure and minimize aircraft turnaround time on the ground so that the operator can turn that aircraft around, get it back into its next flight, deliver high utilization from the asset, and drive cost per ton kilometer down that way. So you're really optimizing for cost per ton kilometer in the given role.
Yeah, turnaround time is always critical in almost any transport. A number of questions are dealing with the questions of regulation. I had to smile when I saw the picture of all the seats facing forward. This is in my view, and I've been told, a hangover from the airliner fixed wingers, because you're going to land in some rapid speed. The airship is never going to come down fast, and it's not necessarily going to come down straight in the nose. So, is this sort of the regulation problems you have to deal with?
Not quite. Not quite, actually. It's a really interesting conversation that we had, or I found it very interesting anyway, as we went into this part of the market. So the question I think you have to ask yourself is, what is going to bring my customers into the pipeline here? What are the things that customer needs to see to understand how something so different fits alongside the fleets that they operate today? And you saw some of the pictures I showed. I'm just going to share here again. Let me get the right screen. I'm hoping you might be able to see that now.
Yes, we can see.
Yeah, so some of the pictures that I showed are a 72-seat layer where the seats aren't all facing forward. And the other ones have got all the seats facing forward. And this was very deliberate on our part to put both of those out into the market, because we think that you can move to some really interesting concepts here. And as you start to think about how do you unlock this sort of traveling capacity over longer sectors, well, make the aircraft a lounge in the sky, make the aircraft capable of being a sleeper train in the sky. These sort of pictures are designed really to unlock people's thinking about what you can do that's different to what we see today. The airline layout reflects the fact that our airline customers have got a business model they understand, they've got a product that they understand, and we're working to position that for them so they can engage with it, bring their own paying passengers on board, figuratively first and then literally, so that we drive that uptake in a way that works with the airline. So it's a very pragmatic set of views about how do you move this into a point where people are ready to adopt.
Well, I'm sure you'll have a little bit more leg room than in a typical 737 that many of us, a little bit taller people, suffer from when we're flying.
It's really, really nice that the laws of logistics follow for passengers, right? So just as you can get lower density cargoes on board an airship, you can get lower density seating on board an airship and make it economically viable.
Absolutely. We are unfortunately at a time at this moment. I hope that you can maybe stay with us, and at the end of the session that we can have a panel and other questions jointly. But I will move on, and I'm sorry everyone, I didn't get all the questions in, but certainly hopefully some of those will be answered in time. And thank you very much, Tom, for being with us and speaking this morning. And I'd now like to move on to our next speaker, who is Octave Jolimoy. I'm sure I've destroyed the pronunciation of your name. He is graduate from the French Arts and Métis Engineering School of Mechanical and Industrial Engineering and Chinese Tongji University in Automotive Engineering. After working for PSA Group, now Stellantis, he joined Flying Whales as a marketing manager in 2020, working more specifically on humanitarian, wind power, and Japan markets. In 2022, he took over the management of Flying Care Project to deploy mobile hospital solutions transported by airships. Certainly, this is a fascinating topic and one that we will certainly look forward to hearing more about. So, Octave, if you are there.
Yeah, I'm here.
Okay.
You can hear me well.
Yes.
And yeah, perfect. So thank you very much for this introduction. And yeah, let me share my screen as well. And let's jump right in. So yes, today we are going to use these 20 minutes to share with you a couple of our ideas about applications related to the rigid airship that we are developing at Flying Whales. And of course, we will make a small focus on the Flying Care projects. So yeah, that will definitely be interesting. Okay, So maybe let's start with what we call in French raison d'être, which is basically the purpose statement of our company. And as we heard also in the presentations before, we are developing an aeronautical solution that aims at contributing to the reduction of cargo transport environmental impacts. So that's definitely one of the major aspects of our project. And at the same time, we are looking to develop a solution to access remote territories. So it's part of the history of Flying Whales to be able to deploy its logistics solution in remote territories, whether it is mountains or territories where there are no roads or no infrastructure, so that no port or no airports. So we are definitely looking to create such a logistics solution to link these territories with the global economy and to be able to provide a sustainable transport solution for them. So Flying Whales is actually two companies, although right now we're only called Flying Whales. And it's a bit of a specificity also amongst other airship manufacturers, because we are both developing the manufacturer and the operator. So on the Flying Whales industry side, we are looking to create 3 production sites. We will see later on where they will be located. And we will manufacture with these manufacturing sites about 160 airships that we will be operating all around the world. So this will be done by Flying Whale Services, so the service company. We will be providing logistics service with this company, turnkey service basically. But we will also use this company as a base manager, because we will have a basis for each of these airships, and also as a training company for all the operators and the pilots we will have to operate these airships. So we are building these 2 companies at the same time, and we will actually be splitting the company in the coming months. So we wanted also to come back on the shareholding structure of Flying Whales, partly because the project is owned at 25% by Canada, by Quebec government. And so we definitely have an important developments coming in Quebec as well, in the northern part of northern territories of Canada, where we will have one of our 3 production sites. At the same time, the project is supported by a lot of French players, whether they are private players or public players. We can see here the Office National des Forêts, which is the first national office of France, which is actually our first client and historic client, with whom we developed the idea initially to be able to harvest some wood in the remote forest of France in a sustainable manner, and without having to build roads, new roads, and other type of infrastructure. We are also supported by large industrial groups such as Air Liquide or Bouygues on specific topics. And now we are working on integrating a new shareholders as well for the development in Asia Pacific. What you see here is the support by the French government as well. So we are funded to be able to deploy the airship for the first flight. So we definitely have a good financial view on what we're doing for the next years. Now, the airship itself. So it's a bit different from what has been presented just beforehand, because here we are developing a rigid airship. So inside of this white frame, there is all the structure of the airship that's made of carbon composite beams. So we use this structure to be able to integrate all the propulsion part and also to secure the cargo, because we can lift up to 60 tons. One of the specificities of this solution is also the capacity to load and to unload in hover flights. So it means we don't need to land. So that's also a little bit different from the hybrid technology we saw just before. So we manage the loading and unloading in hover flights, and we don't need the infrastructure on the ground when we operate. And we also don't need such a large area for these operations. The airship itself is 200 meters long and 50 meters in diameter. And you can see that this allows us to have a large cargo bay. So it's a cargo bay of about 100 meters long, 8 meters in width, and 7 meters in height. inside of the cargo hold and inside of the structure, there are 14 helium cells that are not pressurized. So this is also a specificity of these rigid airships. And for us, it's a safety feature that helps us nullify any aspect of the gas leakage, for instance. We can fly at up to 100 kilometers per hour, and we can fly for up to 1,000 kilometers one way. So these are the features of the airship that we are developing at Flying Wells. It's called the LCS60T. So this is a small video to show you how the operations are going to work out. And yeah, we started the video with a little bit of poetry because we are in France and we like that. But anyway, this is the airship flying off its base. And we will see a couple of operations. So here in the forest, that could be Canadian forest, you see that we hover above an area and we pick up the logs directly with slings and we put them in some baskets we have in our cargo bay. We have a lot of applications related to the wind power industry because wind blades are very long components and also rather light, but very difficult to transport by road. So in our case, we are organizing the transport through the air from one point to the other. So that's usually from the port to the wind farm. We have several applications that are related to construction. So you saw a power transmission tower, and then a lot of applications related to the congestion of ports or the unavailability of infrastructures. So the capacity to unload some cargo from a boat and to the shore is very important to be able to link different islands and to provide a more efficient logistics service without having to build deep water ports everywhere. One of the other segments we investigate is the industrial segment. So this is actually quite fast, but of course, taking a launcher at sea from a barge and taking it back to the shore is something we have investigated in the past. And at the same time, one of the other applications that we investigate is related to humanitarian disaster and relief. So in this case, we provide solutions where the infrastructures are not available, and then we can still operate with the airship. So you finally saw the flying care project with the unloading of a hospital, and then we will review the markets that we are investigating. So inside of Flying Wells, we have 5 main markets that we investigate, and we saw them through the video. So that would be the construction markets, the wood markets, industry with all the industrial pieces, the power markets, and then the humanitarian aid and disaster relief markets. We also have applications related to ports, basically, so decongestion and the transport from boats to shore, as mentioned. And globally, when we investigate these markets and we make market studies related to the capacity of the LCS60T, we come up with a market need worldwide of about 800 airships. So that's from this need that we know that there is definitely a huge potential for these machines. And out of these 800, you saw just before that we are looking to operate about 160. So I won't say much more on the markets themselves, and I will jump to the flying care topic. So flying care's project origin is actually coming from the fact that, as you remember, one of the purpose we have at Flying Wells is to be able to operate in remote areas and to link them to the global economy. And at the same time, we realized in several case studies we made with different clients that we could actually transport almost a building with the airship due to its impressive cargo hold. And so coming from there, we realized that there were a lot of difficulties in these areas, quite remote. So they were, of course, lacking the transport facilities, but quite often as well, they were also lacking the healthcare infrastructure, for instance, or actually a lot of other type of infrastructure. And that's how we begin to investigate the feasibility of transporting a hospital, basically. So everything that you would need in a standard hospital, but transported by airship and delivered anywhere. So that's what we investigated with the Flying Care project. It started about 1 year and a half, 2 years ago at Flying Wells. And we have been focusing on this project on several sustainable development goals. So to improve the access to care, so enable universal health coverage, basically, to build resilient infrastructure, so and to reduce inequalities as well. And finally, we will see at the end of the presentation to build partnerships, because we are only the logistics vector, let's say, of this solution, but we need other partners to deploy such an ambitious program. So if we just give a little bit of insight on what are the facts behind these projects, well, the World Health Organization states several headlines, such as the fact that about 50% of the people lack access to essential health services, and at the same time, there are more than 2 billion people that lack access to safe surgery. So this is actually quite striking, and the WHO is also looking at improving this access and improving surgery for about 1 billion people in its general program from 2019 to 2023. So we see that a lot of these populations are actually located in territories that have a lower access to healthcare, but there are also territories such as Northern Canada or Amazonia, for instance, that are rather developed, but lack access to regular care because they are quite remote and difficult to access. So with the project, we try to aim both at the developed areas where we should have equal access to care, even in the northern part of Canada, such as Northern Territories, and also at areas where it's just the geographical constraints that suppress the access to care, and finally at areas where the development is still not finalized for the healthcare infrastructure, and where we could help support the development of such infrastructure. At the same time, we focus on several types of disease, of course, but we look a lot into the non-communicable disease, so that would be cancer, cardiovascular disease, and other type of pathologies, because they are one of the main sources of death, and that we could inhibit, and we could change with a solution such as ours. So these are the 3 main study zones that we started investigating with Flying Care. So as mentioned, you see in the northern part of Canada, where there is a lack of equipment, but also specialized care and also operating rooms. We also investigated Amazonia. The reason behind Amazonia would be that we had discussions with French Guiana, which is a French overseas territory. And we also investigated applications in Brazil because the constraints are the same. And finally, we made a lot of investigations in sub-Saharan Africa as well. Of course, it's a very diverse zone with different characteristics in different countries, but the needs are there, and the solution we are deploying would be very efficient in several of these countries. Looking at the main challenges that we already kind of saw either in the video or in the OMS statements, a WHO statement, sorry, in English. First of all, healthcare is centralized. So, of course, whether it is because the infrastructure is not available at the area where we want to operate, or whether it is because it actually don't exist at all in the country, several communities don't have access to care. At the same time, implementing new infrastructure might be very costly, and maintaining it is actually even worse. And finally, because of the lack of infrastructure, we have several pathologies that are not detected, so not treated, and that are leading to high morbidity. What we are looking to do is to provide a decentralized healthcare solution. So we mutualize the healthcare facility between different areas, so that we ensure that everybody has equal access to care. At the same time, with the mutualization, we ensure that the costs are kept down, so we become quite cost efficient as an infrastructure for each of our medical tour. And finally, inside of the hospital, we want to ensure high standard medical infrastructure, meaning that we have the possibility of taking safe surgeries, and that these surgeries are available anywhere. This is a view of what it looks like now for the FlyCare Mobile Hospital. You see that it's more than 300 meters square of modular infrastructure, so we will see the modularity just afterwards. But we can basically adjust this infrastructure to the local needs or to the local medical campaigns we are looking to deploy. And the structure itself is like a building, so it's rigid. It means that we can keep a very high standards for the type of the air control, the atmosphere control, and we can ensure the safe surgery parts. So now you see several blocks. So we built this solution around basic blocks that are actually quite big, because each one of them is about 7 meter width and more than 30 meters in length. So it's a big area available for healthcare. And each block has a dedicated function. We will see that right after. So what we are looking to do is to integrate all the type of medical services inside of these blocks, while still enabling remote communication, so that we can integrate telemedicine activities. Because of course, when we are looking at such areas, we know that we are not only lacking the infrastructure, but quite often we also lack the medical teams available. We are looking to operate this infrastructure with local operators and with the authorities, of course, to be able to provide campaigns dedicated to the challenges that these communities face. So this is a small image of what we can do with the modules. So you saw that I explained that we have different types of modules. So we have modules for instance, for consultations, for hospitalization, imaging, pharmacy, laboratory, intensive care, and operating room. And the different modules, they can work either independently or they need to work together. For instance, you cannot really have an operating room without having intensive care at the same time. So depending on what we want to address with the mobile hospital, we can change the modules we put in the hospital so that we can ensure that we answer the needs. So here you see, for instance, only consultation and hospitalization, and here that would be a surgery with 4 operating rooms available in this hospital. Now, this is a quick look at an operational model. So we mentioned that we are looking to mutualize the infrastructure, so basically to address several communities, and with the infrastructure coming back several times every year. So it could be from 2 weeks to 1 month, the infrastructure would be available on site, and the communities around there would be able to have access to surgery, diagnostics, imaging, and other types of specialty care. Then the airship would be picking the infrastructure up and putting it at the next community and so forth, until we reach back the maintenance facility to ensure that everything is functioning correctly, and we can go to the next floor. So doing so, we ensure that the infrastructure is coming back several times a year. So in some areas where such infrastructure do not exist, we can start creating the culture of accessing to the healthcare, which is one of the challenges in these areas. Another thing I wanted to mention is, is that of course we are not working alone. As mentioned, Flying Wells is only a logistics company, let's say. So we gathered some of the knowledge from other companies to be able to develop this solution. So we have a study partnership in place, and we work together with Siemens, for instance, for the medical equipment. This is an engineering company from France that's working a lot on building hospitals. So of course they are helping us with the hospital engineering. Roland Berger is helping us on the strategy part. It's a European consulting group, and some specialized doctors as well are working with us to define what should be in the hospital to address the needs that we want to address. Along this project, we settle as well a community of the wise to have experts to provide us some insight on what we should do in the next years to provide the best solution for the countries we want to operate in. And actually, we also discuss, of course, with a lot of external stakeholders, whether it is NGOs, countries, ministries, or other types of players on the ground. One of the important parts that maybe I failed to mention before is that this project is more aiming at medical developments, so to provide a solution all year round for communities. It's not aiming directly at providing a medical facility in the aftermath of a disaster, but of course, if we are in a region and such disaster occurs, it's also a very interesting solution for this type of theaters. So that's something we are investigating as well. And finally, this is just a quick glance at what we are doing. So it's quite generic, but this study consortium is working at identifying needs, defining the engineering. So what's the design of the mobile hospital, the strategy, and how to organize the operations for the airship and for the solution overall. And then, of course, we have all the financing and business plan parts to be able to set up something that's viable in the long term. So that's the elements that we wanted to share with you. I think I'm almost on time. So yeah, if you have any questions, I would be happy to answer them.
Well, thank you very much, Octave. That was very interesting, and certainly a lot of questions came in from different areas, and we won't get to them all. So, but perhaps you can also address those privately yourself afterwards. You know, this notion of a remote hospital is something we have talked about in Canada, because right now we have to uproot people from their communities at fair expense, fly them down to the south, sometimes with their families. They're here for a long time. There's a lot of disruption. So this notion of being able to take the care to the people is certainly attractive. One thought that occurred to me, though, is I hope you have some kind of a leveling system on your long hospital, because finding level ground, and we don't want the patient rolling off the surgery table in the midst of what's going on. So I assume that's a detail within the actual components that you'll work with. Yeah. One question asked, well, why not bring the patients to the airship? But I realize that's back to utilization and the question that might not be there. The more focused, and by the way, this notion of markets that aren't being served, you've identified a lot of them, you know, things that just aren't easily done today. The moving wind turbine blades, the rocket launching pad, the electric towers, and the mobile hospital. These are all interesting markets. So you're really going to expand the economy in many ways as opposed to duplicating. But all this kind of focuses back on how do you get the cargo on and off? And one of the questions related to this, you know, we haven't seen this explained or demonstrated. How exactly do you change these loads and buoyancy? And could you address that question?
Okay, so yeah, I didn't see the question, but I will try to answer it in the best way. So yeah, of course, we are loading and unloading a lot of different types of cargo. And so what we have, we can think of the airship, the LCA-60T that we are developing as a very large flying crane, basically. So of course, depending on what we load, we need to adapt to these loads. So we have specific designs and what we call toolings to be able to adapt to these loads. So we know that a given airship, when it's at its base, it will not operate on a single market unless the market activity is sufficient, but mostly we will be able to provide services for different types of markets. So we know we will need to adapt the toolings and have several availables at our base to adapt to all the markets. So that's how we manage to take up all types of load. And actually the mobile hospital is quite unique because it's already being designed to be lifted by the airship. So I guess it's one of the first industrial infrastructure that's being designed for this purpose.
Yeah, it's certainly very interesting. And one of the other questions that came in dealt with this question of, you know, in the pictures, you see them coming down without any winds. They're nice and coming down, but wouldn't there be some pendulum effects you have to deal with as well?
Yeah, definitely. There are some pendulum effects. So we do have some systems that are developed within Flying Wells internally to manage these effects. And there are actually some IP on these systems as well. So yeah.
There were some questions coming up about helium and some responses back into the chat. So I don't know how much we want to put the question to you, but 800 airships will take a lot of helium. Certainly Eli didn't think there was enough for 25,000, and I'm sure that somewhere in between there is the answer. But does helium availability and cost concern your operations?
Mhm. So yeah, we know that there is actually large helium supplies available. So and at the same time, for us, helium is mostly stored. So we do have a little bit of leaks, of course, because it's a very light gas, but most of the helium will be stored. So on our side, the analysis is that the helium necessary, for instance, for the medical is a much bigger market than the one we will have with the 100 airships that we will be deploying. And at the same time, you know, things are probably going to change in the years 2030, with also large scale storage of helium in the US and in Qatar and in other areas. So no, we don't really expect to have a problem with that.
Okay, and some other questions came up about, you know, winds and the speed. And again, clearly there's days you're not going to be going places. So, you know, in terms of emergency delivery, I suppose that is something that you have to be concerned with in terms of reliability of being able to do that. Let me see if there's some other questions that not sure if I had more for you.
On the winds part, it's interesting because you know, I think it's one of the strong aspect of the Flying Whales program. It's the fact that because we are building both the manufacturer and the operator, we take the constraints, the wind constraint, both on the design part and on the operating part. So we really have to settle both problems at the same time. And we develop right now internally all these tools to be able to assess what are the flyable days and when they occur, if we actually can fly. So yeah, there are a lot of tools to deploy on these aspects as well, and we do that internally.
But given that you're very unique in terms of what you can do, I suppose the shippers might be more patient if there's no other way to move that power for the electrical systems into place. They'll do it when the wind is right, and so on. So clearly the markets will determine when you can operate and so on. I see we're now at the place of our time is out, but I hope that you will stay with us, and I'd like to bring the panel together next, and our next speaker promised to be a little bit shorter anyway, which is good, and we'll have everybody back at the end for some questions. So thank you very much, Octave, and again, I'll let you answer some of the questions that are in the chat directly as well.
Okay, thanks.
So, thank you so much.
Oh, sure.
And I'd like to now introduce my colleague, MALALGODA, who is a professor at the University of Manitoba with me and a member of the Transport Institute. And NARENDRA, I'll turn the program over to you.
Thank you, Dr. Prentice, and good morning, everyone. We've had a great session so far, and we discussed a lot about airship development and different types of airships. And now we are going to have a couple of speakers and discuss about the hydrogen technology, which is crucial for this industry. So without further delay, let me introduce our first speaker, Matthew Klippenstein from the Canadian Hydrogen and Fuel Cell Association. So introducing Matthew. Matthew is a fluently bilingual chemical engineer who has worked in British Columbia's clean energy economy for the past 20 years. In addition to this, in addition to his extensive hydrogen and fuel sector experience, he worked as a consultant in Wood's Renewable Energy Group, performing energy yield assessments for wind and solar projects. As Executive Director of Hydrogen BC and Regional Director for Western Canada, Matthew oversees advocacy, marketing, communications, and government relations for the sector in BC and Western Canada. Matthew, the floor is open for you.
Thank you, NARENDRA. I just want to check, am I coming through okay for everyone? Yes,
Perfect.
okay, I'll share my screen then. Yes, so thank you very much for having me at this Airship Summit. This is a discussion on hydrogen applications and future uses for in the context of airships and other transport generally. There's a little introduction to myself. So I got a chemical engineering degree in 1999 from UBC. I spent about 15 years in the hydrogen fuel cell sector. I had a very small, very financially non-rewarding detour into theater. very temporary. I started to look at Canadian electric vehicle sales in about 2013. So I was the first person to start writing about that online. As noted, I spent a bit of time in renewables, and as well spent a year and a half at a nonprofit helping lead outreach and administering the province of BC's rebate program to put electric vehicle chargers in the shared garages of apartments and condominiums and townhouses. So I've been back in the hydrogen space for a few years now. And in terms of hydrogen, just do a super brief sort of 50,000 foot kind of a preview. So hydrogen's has been newsworthy for the past few years. And that's mainly because governments have started to talk about net zero targets. If you're aiming to reduce emissions by 20, 40%, you probably don't really need hydrogen for that. If you want to get to net zero or reasonably close, you need a whole bunch of clean hydrogen. In a net zero world, the dominant energy carrier would be electricity, and hydrogen would be kind of the sidekick. Used an analogy here with the lobster claw, where again, most of the heavy lifting in energy provision and emissions reductions comes from clean electricity, with hydrogen filling up the rest. And there's some estimates on what hydrogen's share will be in different regions of the world at that point. Bunch of different ways of making hydrogen. What we have historically, maybe moving up from the bottom of this slide, we have steam methane reforming. So that is the use of natural gas in a reforming process, which produces hydrogen, but also a lot of CO2. That wasn't really a big deal back in the day before we priced carbon. Now we are pricing carbon more aggressively, and there are processes to make hydrocarbon-derived hydrogen while capturing up to 98% of the carbon dioxide. And the incentives are in place. That's kind of the path going forward. You can also make hydrogen from pyrolysis, which is the reaction of the decomposition of natural gas in the absence of hydrogen, in the absence of oxygen, sorry. And here, instead of making hydrogen and then carbon dioxide, you get hydrogen and then carbon powder. So this is a pyrolysis technology. The largest facility in operation today makes about 10 tons of hydrogen per day in this manner. And then they sell the 30 tons of carbon black, this industrial material, to tire manufacturers. So it's an additive for tires. You can also make hydrogen with biomass gasification, very relevant in many parts of Canada, and also from electrolysis. So the use of electricity, preferably clean electricity, to split water with the use of electricity to form the hydrogen molecule. A bit about us as an organization. So the Canadian Hydrogen and Fuel Cell Association, we are currently trying to figure out a rebrand so it's a little bit less bulky of a name. We're a pan-Canadian organization. We have affiliates in BC, that's me, in Alberta, Ontario, and Quebec, and there's a group out in Atlantic Canada as well. We recognize that different regions will have different priorities or different best paths for scaling up the use of clean hydrogen. We have members across the value chain, and we have had some success with government in our interactions with them. And it's a very positive and inclusive approach, kind of like how I suppose airships can happily coexist with aircraft. This is a little scan of our members at a glance, just trying to say that we have everyone from energy producers and industrial gas manufacturers to infrastructure folks, fuel cell and hydrogen engine makers, as well as vehicle OEMs. I suppose perhaps we'd hope that as some of the airship companies get rolling or get floating, that we'll be able to add them as vehicle OEMs as well. Just a little eye chart on the members. If you ever want to play Where's Waldo with some company of note, you can go through this eye chart here. One comment that we like to make in our hydrogen policy discussions, and this may be quite relevant in the airship space with respect to remote communities, is that a lot of policy recommendations come from well-intentioned folks in Western Europe. Western Europe is about as big as Canada, but Canada has like 7% of the population, and so what seems like a wise or a slam dunk thing in a European context is often completely non-applicable to Canada. So maybe this slide might be of relevance with some folks in the space, especially dealing with Arctic communities and so forth. Canada-wide, so hydrogen does have a number of roles that it's likely to serve in a highly less lower emissions society. It is already used as a feedstock in some industrial processes. The dominant use of hydrogen right now is to make ammonia for fertilizer, feeding people, very good thing. A lot is also used in the upgrading of hydrocarbons, like oil refining. And a new application for hydrogen is to replace coal in the reduction of iron ore to iron in steel making. So when you use coal, you convert iron ore to iron, get rid of the oxides, but then you form CO2. You can use hydrogen to do that, and you form water vapor instead. That is a use case that's likely to scale up a lot in Ontario in a number of years' time. It can be used for heat and power as well. We'll get to that in the next slide. And airship relevant, it can be used in transport. It's got some, this is a nice, interesting battery versus hydrogen trade-off, which may be of relevance to you guys. Moving to the heat and power first, again, thinking about the Arctic and Canada's fairly northern climate, we use a phenomenal amount of natural gas energy over the winters to stay warm. Battery energy storage is fantastic. It's great. We'll be able to do a bi-directional connection between electric vehicles and the grid, growing at some point, but we're always going to need a lot of gas energy to heat ourselves in the winter. Today it's natural gas. In a more emissions priced world, that'll be clean hydrogen. I do hope that, much as I believe the last speaker had mentioned 94% accessibility of water, we kind of hope that we can get 94 or higher accessibility with hydrogen. Kind of our one of our long-term goals. In terms of the use in transport, an analogy I've used, which seems to resonate with people, is that batteries are a little bit like exoskeletons. If you're a small creature in nature, chances are you've got an exoskeleton, maybe a shell type of exoskeleton. And that's because at a small scale, there's nothing that can beat a shell on strength to weight ratio. The corollary is that all larger creatures, from a cat on up, tend to be vertebrates. They have an interior skeleton. Endoskeleton. And so in transport, we see things having a similar kind of approach where battery solutions are likely to be dominant on the smaller side, the smaller vehicles, some larger vehicles as well, some buses and trucks, even some short-range ferries perhaps, with hydrogen taking the larger set of the, I guess not of the animal kingdom, but of the transport kingdom. In some cases with airplanes or with boats, it might be a liquid fuel derived from clean hydrogen, ammonia perhaps, or some sort of synthetic fuel. Airships, I promised to put a blimp up here once I can find a little graphic. So just let me know if you guys have some good icons out there. One other thing I want to leave everyone with, hydrogen is quite niche, it's gotten a lot of attention now. There is a reason for confidence and celebration in how the use of hydrogen is gradually scaling up. From my time doing work in the wind energy sector, I had plotted out the growth of the very earliest wind turbines, turbine deployments in the 1990s. This is the very earliest phase of the wind industry. And it rose, I think this is a logarithmic chart, but rose maybe ballpark on the 30% a year over year basis. And if you overlay the solar scale up, but just shift it by 8 years, so instead of being the 1990s, it's the 2000s, you can see it, the legend on the graph there. The solar photovoltaic industry grew along a very similar trajectory. It's kind of neat, nice coincidence. I spent a number of years in fuel cells, hydrogen fuel cells, and those too are following a very similar trajectory as the solar and wind did. It's just the fuel cells are like about 15 years slower than even solar. So 15 years after solar scaled up, which was itself 8 years after wind scaled up. And the most interesting thing in terms of hydrogen production from electrolysis, splitting water using electricity, is that this is this purple chart here. Electrolyzer production is scaling up faster than these other prior technologies, which is a good reason for enthusiasm. Don't want to celebrate yet, I suppose, but should be an indication that for folks who are looking at hydrogen as a propulsion fuel, possibly even as a buoyancy gas, there will be a lot more clean hydrogen out there soon. I use this slide in my outreach with like city councilors and things like that. I guess I should emphasize that it's actually burning blimps, not just blimps themselves, that people think of when they think of hydrogen, and we're trying to have it recognized as a core climate solution here. I think the last slide I want to leave everyone with, this is probably a very similar this may be a similar analogy in the airship space, is that hydrogen today is a bit like cell phones, mobile phone networks 40 years ago, because at the time there were no networks. It was, you would have maybe a city would have one cell phone network going along the highway to the downtown core to wherever it was that rich people lived. Cell phones were more expensive, bulkier, terrible phone quality, didn't have very good data transfer. And you also had a lot of improvements happening on the landline space. So a lot of folks underestimated just how much cell phones would grow because there was no network to begin with. McKinsey made a very famous sort of business study flub. And a very similar thing is likely to happen with hydrogen, as we don't have much of a network now, but it will scale up, and new uses, perhaps airships as well, will find their strong spots. And I think that is, yes, okay, this is just my final slide. So I will try and figure out how to return this off of the shared screen, and I'll turn it back over to Narendra.
All right, thank you very much, Matthew, for the very interesting presentation about the use of hydrogen. And I think we have a couple of questions. I think the first question was partly addressed where they asked about any new technologies for splitting water or seawater. I think you mentioned about the electrolyzation production. I think that's something that's going on. Anything you want to add to that?
Yes, so there was a recent paper out in the journal Nature from a Chinese group working on the direct electrolysis of seawater. So no pre-treatment of the seawater to go into the electrolyzer. The short version of it is that they came up with a very elegant engineering way to be able to use very impure water inputs for this electrolyzer technology to reduce the cost of actually generating the hydrogen. No need for pre-treatment. They are starting to deploy that. Hopefully it works in real life as well. But yes, so many reasons for enthusiasm for our ability to create clean hydrogen to assist with decarbonization, grow jobs, shrink emissions. And yeah, I suppose in part this is the inevitable result of sort of carbon policy, because as soon as you put a price on pollution, then folks find solutions for that.
And one more quick question before we move on. So I think with the increased use of hydrogen, you showed in your presentation, we are using hydrogen for many other purposes. And of course, we are thinking about the potential of using hydrogen as for airship technologies as well. So in future, we might need to store this, right? So when it comes to storage, what are the cheapest bulk storage options for hydrogen, and what about long-term storage when it comes to hydrogen storage? Any
Sure.
thoughts?
So I'll take the second part of the question first. So hydrogen can be stored underground in caverns, much as natural gas is stored today. There are actually 3 hydrogen storage caverns already in use in the United States. Now, this is before carbon taxes. These are to supply the petrochemical industry in case like a steam methane reformer goes down. So we already have a mature, well-established way of storing enormous amounts of hydrogen underground, much as we do with natural gas. We would need, pipelines as well. We have a couple of short pipelines in Canada. In terms of storage for like fueling and so forth, on the road transport side, maybe with locomotives as well, the expectation is you'd store a liquid hydrogen. A bunch of disadvantages to that, but there are some advantages as well. You don't have to wait for pipelines to be built, for example. In the airship context, I'm not sure what, I guess it might depend on how much hydrogen would be used on the flight to determine how one might bring the hydrogen to refuel the craft or refill the craft, perhaps.
Okay, thank you very much, Matthew. Well, if there are any other questions in the chat, feel free to answer those.
Sure, I'll take a look in there.
Yes. So without delay, we'll move on to our next presenter, is Austin. So let me introduce Austin Brittenham first. So Austin is a JD candidate at the University of Mississippi, where he will receive a concentration from their Center for Airspace and Law. His legal research covers issues in domestic and international air and space law related to emergent technology, business, civil rights, and legal theory. Prior to law school, he worked for a multinational technology company in technology entrepreneurship and higher education. Outside of the classroom, he helps small nonprofits through board and advisory roles. Austin, the floor is over to you.
Thank you. I appreciate that introduction. My name is Austin Brittenham. Like I was introduced, I'm a current student at the University of Mississippi in their Center for Air and Space Law. My previous research has been on the legal status of hydrogen as a lift gas in fuel ships. As a lift gas in airships. I wanted to start with a value proposition, but I think that that's generally been covered both this morning and yesterday. That is, airships enable things like major carbon savings associated with air travel, cost savings for certain kinds of cargo shipping. They can enable better last mile delivery, unlock new markets, and they can reduce landing infrastructure needs as well as aid in humanitarian moments. Some quotes that I had in my presentation, I wanted to thank Tom Grundy, who's no longer here, for having written them and made their way into my legal publications. The barrier to some kinds of airships is currently the cost of helium. So some airships companies have elected to move to hydrogen. In the United States, we see H2 Clipper sort of leading the way in that way. And it's produced by this contemporary difficulty surrounding helium. Helium is about 67 times more expensive than hydrogen, at least at the time of my writing. And when the last legal writers were considering hydrogen versus helium, they were writing in the early 2000s, where there was only an 8 times difference in price. So they speculated that no transition would be desirable nor occur because of the non-flammable nature of helium, meant that hydrogen was perceived as less desirable, even though it might be, even though helium might be more costly. Since then, the cost of helium has dramatically increased, like I said earlier. And so I think that there's renewed interest in whether or not hydrogen could be a viable lifting gas solution. That brings me to the institutions that govern laws. So I want to start in supranational organizations. Those are the organizations that sit above any individual nations because they are made up of a collection of nations. You have the International Civil Aviation Organization, or ICAO. Their mandate, their purpose is a specialized agency of the United Nations that coordinates the principles and techniques of international air navigation and fosters the planning and development of international air transport to ensure both safety and orderly growth. For non-legal folks, nations implement these ICAO standards and recommended practices, which are called SARPs. And these are technical specifications adopted by the Council, so adopted by nation states, and then promulgated through their domestic organization. So ICAO currently oversees over 12,000 SARPs related to air transportation. And they've published annexes to international air transportation treaties, and there are 19 of those that also amend the existing treaties. There's also national implementation of procedures for air navigation, or PANs. These are documents approved by the Council of ICAO and are recommended to states for worldwide adoption. The reason I'm talking about this at all is that ICAO is responsible for what some of you who have flown airships or worked in the industry would know, certificates of airworthiness. That comes from ICAO's mandate. So individual nations have to create registries of aircrafts, which they determine how to in their own way. But generally, these keep track of any individual aircraft and whether it's worthy to fly. The other thing ICAO does with respect to certification are type certificates. So when a new kind of aircraft, like say a Boeing 737 has been developed, ICAO reviews this kind of aircraft for safety to determine whether this kind of aircraft is suitable for air transportation around the world. And there have been very little updates to type certification in the last 20 years, though there's been a small amount related to airships. So ICAO's global definition for purposes of airships, I saw some conversation in the chat about this. For international law, an aircraft is any machine that can derive support in the atmosphere from the reactions to the air other than the reactions of the air against the Earth's surface. So this covers nearly all kinds of aircraft except hovercraft. And airships certainly fall into this category. Next, in international law, there are balloons, which are non-power driven, unmanned, lighter than air craft in free flight. And so while an airship might be lighter than air, it is neither importantly is not in free flight. And so for purposes of international law, airships are not balloons. And then aeroplanes are heavier than air vehicles with a few other qualifications. And so that itself does not describe most airships or any airships to be precise. And so airships for purposes of international law are not airplanes. I have this document I wish I could share. It's a very busy chart about how regulations are determined or promulgated, formulations of SARPs and PANs at the international level. But I'll save you all sort of the description. The purpose really is that there are laws, rules, and regs that have to be implemented at the domestic level. In the United States, the FAA is responsible for doing that. And in Canada, it's the Transport Canada Civil Aviation. In the United States, which is where the primary focus of my research is, airships designed for hydrogen, airships lifted by hydrogen cannot be issued a certificate of airworthiness from the FAA. There's two reasons for this. The first is that the airship design criteria, subpart 4448 of the FAA in 1995 still governs current design criteria. And they indicate that no lifting gas, or that any lifting gas that is to be used must be non-flammable, which excludes hydrogen. And the difficulty then is that without a valid certificate of airworthiness, it's illegal to fly a craft under 14 CFR section 91.203. So either a hydrogen airship would have illegally or fraudulently maintained a certificate of airworthiness, or it would be a craft flown without a valid certificate, which would still be illegal under a previously cited law. So in neither way does the current legal environment allow for hydrogen-based airships in the United States. In Canada, the Airworthiness Canadian Aviation Regulation 541.7 indicates that a lifting gas, regarding lifting gases, indicates that hydrogen is not an acceptable lifting gas for use in airships. And this creates an international legal problem because the European Aviation Safety Agency, EASA, created a certificate for airworthiness programs for airships. SC Gas 2355 in many parts, Part B for our purposes indicates that if a lifting gas is toxic, an irritant or flammable, adequate measures must be taken in design and operation to ensure the safety of the occupants and people on the ground and all envisioned ground and flight conditions, including emergency conditions. So the implication is that hydrogen can be used as a lifting gas, even though it's flammable, as long as safety provisions have been put in place, both in design and operation. And the international difficulty that this creates is that nations are compelled through international law to recognize the validity of aircraft certification that has been properly done by another country. So any hydrogen airship granted a valid certificate of airworthiness through EASA could fly to the United States, but while in the United States, its certificate for airworthiness would violate US domestic law, and the US would also be compelled to recognize this certificate as appropriately handed out through EASA. And so it creates sort of this international law difficulty. I have some thoughts about how that would play out if it were ever to arrive in court, but I'll sort of save that for our audience here. Instead, I have a series of recommendations that I think would shore up this problem. One would be that the international group ICAO, the Secretariat could initiate a proposal for a new standards and recommended practice with respect to either contemporary airships generally or to lifting gas agents in particular. The ICAO has ICAO has provided very little updates for the laws, regs, and SARPs and PANs associated with airships because there hasn't been nearly as much demand as the other kinds of craft that they govern. And so this has really sort of fallen off their radar for quite some time, but the players in today and yesterday's conversation, as well as emergent players, might change that lack of interest. For the United States, there would need to be a review and modification of the design criteria banning lifting agents, and that is possible. For instance, there could be either a review that found, similar to EASA's gas, that flammable lifting agents are viable or valid as long as there's sufficient operational and design criteria that would protect passengers and operators from any associated risks. And similarly, the FAA has already commissioned in 2019 a report on hydrogen as for fuel cells in airplanes, where they published a 257-page report, which suggests that they're at least aware of the technical requirements associated with hydrogen for purposes of other kinds of aircraft. So they might have technical expertise that would lend themselves to this kind of research a little faster. In Europe, the United States, Germany, and the Netherlands have an existing airworthiness requirement agreement that also bans the use of hydrogen. And so this agreement would need to be revised or suspended in light of these kinds of changes, because even if the United States were to legalize hydrogen as a lifting agent, those kinds of crafts would still be inoperable or invalid to fly in both Germany and the Netherlands based on this existing agreement, and vice versa. So to enable transcontinental cargo between select European nations and the United States, some amount of legal tidiness or cleanup must be done. So thank you all for sitting through a little legal talk with absolutely no visuals. I appreciate you all hanging in through the technical troubles I experienced, and I'm ready to take on any questions.
All right. Thank you very much, Malcolm. I apologize the panel members. I was looking at the other chat, the questions. So I think I might have missed a few questions earlier too. But I can open the session for any panel member to ask any questions from Austin. And after that, if we have time, we can go to Matthew again as well. Any questions from the panel members for Matthew or Austin? We are right about, we are on time. So
we are on time, Narendra, but we do have the ability to go a little bit over if there are questions. And certainly this issue of the legality of hydrogen is one that I've looked at as well. It seems to me that the decision to ban hydrogen was not based on any legal or engineering, any scientific or engineering study. It was a political decision made in the US. To what degree can scientific evidence challenge these kind of legal issues, Austin? Or does the government have any obligation to actually develop a reason why they've banned something?
I can't speak to their requirements at the time that hydrogen was made illegal. But what I can do is speak a little bit to how it operates now. So at the international level, if that were to be the process by which this problem is resolved, ICAO has a subset of folks involved in research that are made up of technical specialists from around the world, and they review a proposed technical requirement, either a restriction or admittance of the technology. And so these are folks who work very hard over many years to determine whether a technology should be regulated, or in what ways, and in what ways would it be feasible to regulate a technology. That gets passed to the members of ICAO, nation states, the representatives, to actually vote on. And if it passes, then it must be implemented or promulgated through the domestic regimes. So in that way, science and good science plays a very critical role, though there still is some amount of politicking that happens there in terms of which nations are voting for what technologies. But it's a independent group of technological experts, and it's commissioned based on the technology. So it's not just five folks every time who are the same, but quite literally hundreds of scientists from all over the world, and they vary by the technology. In the United States, that's different. Depends on which transportation group. So in this case, the FAA. And they regularly also use good science to inform their decisions, but they are also not totally immune to politics either. My hope is that some of the forces you've described, Barry, and I've read through your work, that disabled hydrogen are gone, some of the political and financial interests. And also, at the time that hydrogen was made illegal, airships were a more nascent technology. I think when we think about the fraught history of air, heavier than aircraft, planes especially, they were very risky and unsafe in their early days, and good regulations has created the possibility for air transportation as we know it. And so in my mind, the solution is not the banning of hydrogen as lift gas, but correct and technically appropriate safety measures that make it safe, so that we can get hydrogen-based airships for those like H2 Clipper who are trying to bring it to market.
Narendra, do you have some more questions in your?
we have a couple of questions in the chat. Austin, can you see the chat?
I can. I'll go in order that they came in through. So I see Joel first. What I might think about the outcome of a legal challenge of flying a hydrogen-lifted gas airship into the United States. This has happened one time before, where an airship, or not an airship, excuse me, a aircraft, it was kind of plane, certificated in one country, was flown into the United States. It was a case in the 70s. It worked out favorably for the foreign company flying their craft in. So my thought is that it would be an expensive legal challenge that could just never have to occur in the first place, but that I don't know, it should totally scare off businesses at the prospect that the US just might be off market. I think the US market might be sort of compelled to recognize the certificates of a hydrogen-based airship. Miles asks the question: any any indication on the FAA's willingness to adjust course on hydrogen as a lift gas, given that flying whales, HAV, and EASA are aware? Am I aware of any American developers pushing for certificate criteria in the United States? So the type criteria is actually handled at the international level, and I've got some folks over there who I chatted with, and my understanding is that they haven't thought of it. They haven't really needed to. No one's at the international level has been pushing for hydrogen airships. In the domestic market, there's a California-based company, H2 Clipper, that holds many patents for both hydrogen airships as well as sort of hydrogen delivery technologies for other for like offloading hydrogen from the airships, updating existing natural gas lines for the movement of hydrogen and stuff like that. So their business is really moving on hydrogen. I chatted with their CEO, and my understanding is that they're not targeting the international government. So that for purposes of a type criteria, the kind of aircraft that would have to come at the international level. At the domestic level, changing the US laws that foreclose hydrogen, I think that they are working on that now, and I don't know the FAA's current inclination to change or not change.
And Austin, we have another question and answer chat, and I see a question regarding the legal basis. Do you have any idea about the legal basis of transporting hydrogen as cargo? Is there any basis on that?
Yeah, so I've published a legal paper on this for folks who might want to read it. You can send me an email, find me on LinkedIn. But I kind of joke in this paper that you can move hydrogen on an airship in like a hydrogen fuel cell, or you can use hydrogen fuel cells to generate electricity to move the airship through, anything besides lifting. And in fact, in some circumstances, you'd have more hydrogen in like a cell than you would need to lift the gas, or that you would need as lifting gas to actually create vertical movement. And so I think that leads a lot of people to wonder if these are silly or no longer, that these kinds of laws and regulations no longer serve their purpose.
Okay. I think we've answered quite a few number of questions, and I think with the time duration, I think we can come to an end. So thank you again, Austin and Matthew, for your wonderful presentations. And if anyone needs to clarify anything further, please feel free to contact them. And I think Austin will share his presentation later with everyone. So with that, I'll invite Dr. Prentice for the final remarks of the workshop.
Thank you very much, NARENDRA. And I realize we're a little over time, so I'll keep my remarks short. First of all, just thank you to all the panelists who presented and for taking the time to make the presentation. I've felt that these last couple of days have really provided us with a lot of new information, and also reconfirmed some of the things we thought perhaps, but nonetheless given us a better picture of where the airship industry is at and why we actually need it, and how we might go about it. Again, I also wish to thank our chairs who've served us very well. I was remiss in not mentioning that Nathan Smith was supposed to be chairing the morning session, but James Smith got in the road. This is his new son, born only a day or two ago. So logically, Nathan has other things to do besides chair the session. So that's why I appeared here this morning. And also thank you to the University of Manitoba and the Transport Institute for supporting and funding this operation, and for all of you who came. We very much appreciate that, and our hardworking technical person, Chris, who's keeping everything going. So again, thanks to all who came. I would again reiterate that there is going to be an in-person conference in Nuremberg in Germany at the end of September. I think it's the 28th, roughly. And I hope that some of you can make it. Certainly you'll have a chance to perhaps ask some of these penetrating questions one-on-one with the airship developers themselves. So with that, thank you very much, everyone, for coming and attending. We are recording the sessions. They will be available. I will be sending you a link so you'll be able to have access to them. And thank you once again for your questions and attendance. And I'll say, yes, bye for now.